So, all right, so closure, we're gonna walk through closure right now. So we've talked about this, we've brought it up a few times, but it's just one of those things that it's helpful to hear it a few times and to work through it. So the idea behind closure again is the first thing is you're working with higher order functions. A higher order function is a function that either receives a function and or returns a function from it. And so closure pertains to higher order functions. So this concept really only comes into play again when you have a function being returned from a function. And so just the main idea behind it all is just that the function that gets returned can go back and look in the higher order function. That's what it is. So what it means is that in the higher order functions scope, we can create some variables that give kind of an external state to the function that's being returned. So because a function, when it runs, it opens up, executes all the code, it closes, and then any variables or whatever that were inside of the function, they're gone. Unless there's some type of external reference to them, but they're gone and they're removed from memory. And so with the counter, so the idea with closure is that you have this function that's returned, can be run, it can be opened, it can be closed, but then it can have these variables that it references in a safe spot that it can modify, and it adds like this private state to these functions. But that's kind of wordy, used a lot of nouns. I know that it's hard to follow these verbal explanations sometimes, but we'll walk through it and explain it. So, all right, so counters. So the point of counter is that I want to be able to create a counter like this, and then when I do every time that I invoke this function, it's going to return a different value. So it'll return 1 there, it'll return 2 there, 3, 4, 5, which is interesting. Like it's, to mentally try to create a function that is going to give a different output, each time we invoke it like this, that's a little bit trickier of a challenge to think about, just because a function, again, when it opens up and closes, all the variables that it has will be removed from memory when it closes. And so so the function itself that's returning the number, it needs to store the number in a place where it's not going to get removed from memory when the function closes. So the way that we do that is, instead of counter, we're going to define a variable inside of the counter scope. And I'm going to say let counter equal to, say 1. So you can write this a couple different ways. It's weird indentation. Okay. And then we're going to return a function. So right here we have this anonymous arrow function that's being returned. And then inside of it, we can reference this counter variable that we created out here on this in this scope, in the parent scope. So this anonymous function, again, doesn't need a name, because when we invoke counter right here, this function's what's going to be returned, and it will be assigned to this variable. So this function doesn't need to have a name in this scope, because we're never referencing it anywhere else. We're just defining it right here, and then it's going to be immediately returned and assigned to a variable out here. So we can kind of walk through it, get it working, and then we'll go back through and then kind of read it step by step, line by line, and analyze what's exactly happening. So inside of this function, we're just going to say, well, actually, let's do this. Let's do, I'll make this 0. Let's do counter plus plus. So then we're going to increment the counter, increase it to, just increase it by 1. And then we will return counter like that. So I'll go through this in like ES6 code optimizations we can do here that maybe you're spotting, but we'll go back through and walk through those in just a minute. So, all right, so now, yeah, so we have our counter that's being printed out. Something that I'm going to do is I'm going to just throw in a console.log right here. So that way I don't have to wrap each one of these functions down here in a console.log. But so I'm going to do that. Now let's run this. And we see 1, 2, 3, 4, 5 is printed out to the console. So, and again, if I pull the console.log out, like, let's console.log the result of this. So we'll just see the 5, but we'll see that it was successfully incremented up to the number of 5.
A quick question, Ben.
Yeah.
Just the naming it the function counter and the let variable counter, those two are completely unrelated to each other, right?
Yes, they are. Yeah, that was bad. Yeah. There we go.
Gotcha. Thanks. I was just throwing.
That reads a little better. That reads a little better. Yeah. No, that was a confusing way to write it. So yeah. Okay. So we have this counter function. Okay. So let's walk through this now. So this is how the computer is reading this code. So again, we always start from line 1, and it's left to right. So const sees the const keyword. It creates a reference called counter, and then it assigns it to whatever's on the right of the equal sign. The whole unit, the whole thing on the right side of the equal sign is everything from here all the way down to here, to the semicolon. So all of that is assigned to the variable counter. Okay, so we come down here, and we see, okay, const, we're creating another reference. So you go my counter function. Okay, so we create a reference in memory called my counter function, and then we assign it to this. Okay, so we see counter. So we go up and reference the counter variable here. We grab this function. So, and it's not really grabbing it and moving it around. It's just saying go to this place in memory and like use this function. So we're going to use the counter function, and then that's what the open and close parentheses mean. That means call the function. So if we remove this right here is just a it would now make it so that way my counter function and counter are both variable names that are referencing the same function. So like if we're going to make a diagram of this, so now you guys get to see my horrible annotations. So so essentially like this variable right here, counter, so if that's this little rectangle, we're assigning it to this function in memory. And then down here we're saying my counter function, if we remove the parentheses, there's no parentheses there, that's essentially like saying, all right, my counter function is also a reference to the same object. So that's what this is doing right here. If we put the parentheses on, what that's doing is we're actually invoking we're actually invoking the function, and then this variable right here, it's not going to be a reference to the function code, it's a reference to whatever value, is returned from, the function after it executes. And so this is something that surprisingly a lot of, or not, I don't want to say it that way, it's just something that can be tricky to have an intuitive understanding about initially. So, all right. Can you guys still see my screen? Everything kind of like went funny for a second with Zoom. Just like sanity check.
Yeah, yep, still see you.
Okay, great. So, okay, so all right, so counter, we're going to invoke it. This function's going to be returned. Okay, so we're going to go in and then run it. Let's see. Okay, I'll walk through those questions in just a moment. So we're going to invoke counter. So counter this function right here, we're calling it. So again, left to right, there's no parameters. You come in, okay, so let count. So we define a count reference that will live inside of this function's scope. So this is where it's contained. So the count variable is inside of that function scope. We assign it the value of 0, and we come down, okay, return. So return, that means this function is going to end, and then we're going to return or give back a single value, whatever is to the right of the return. And so the thing that's to the right of the return is this entire function. This entire block of code is what is to the right of the return. We've broken it onto multiple lines, but this is the thing that's getting returned. So this function is essentially what's going to be put right here. So like this is going to be, you know, the function code. Like this is just like a note. This is like just like my pseudocode. But like, so my counter function is a variable that refers to this now. So this is a common pattern where you have a function that returns a function. So my counter function refers to this right there. That's what this right here is doing. Counter, it invokes counter, and then it returns this function, and then my counter function is going to be a reference to that function in there. So my counter function, it's like conceptually you can think of this as like it's doing the exact same thing as like up here where we say const counter is equal to the function. Like that's what we're doing right here. It's just that there's this function call that's returning the actual function that's going to be on the right hand of the assignment. So, okay, so just again clarifying that this reference here, this variable, my counter function, refers to the function that's being returned. And again, I'm going like pretty slow here, but I'm just trying to be very, very, very thorough with this. Okay. So this first call of counter is giving us a counter function. So my counter function right here is a function. It's not a variable. It's not a number. Or I mean, sorry, it's not a number. It's not any other value. It's a function. And so then we're going to invoke it right here, my counter function, which is going to call this function. So we call it right here. So my counter function, so we go up and see, okay, so we get to this line, the system gets to this line, it sees a reference to my counter function that we're invoking. So it says, okay, where's my counter function? It's right here. Okay, we're invoking it. What are you equal to? Okay, so you're equal to this function right here. So we're going to run it. So we're going to come up, okay, no parameters, come down to line 1. Okay, so count. We need to increment count. So, all right, so it's going to look for count. All right, is there a count in this scope? No. So it's going to go look at its parent. All right, do you have a count? And then, yes, there's a count right here. Okay, I need you to increment plus plus. So this increases to a 1. And then it moves on to the next line. Okay, return. We're going to exit. And so then it's going to take count. All right, do I have a count in here? It's going to look and says like, okay, I do not have a count that is defined in this scope. There's another reference to a count that's already existing, but there is no definition. So it's going to go back up and look up here. And it's going to say, oh, okay, there's a count right here that's defined. It is a 1. And so I'm going to return the 1. Okay, so now we come on to this next line. My counter function, again, we go up and invoke it again, this function in here. So again, it looks like no parameters, we come in. All right, so count, go find count. Oh, it's up here. Change, it's a 1 at this point, so let's change it to a 2. And then let's come down and then we'll say, all right, let's return count. So go find count. Okay, count is 2, return 2. Same thing here, run the function. Okay, go find count, make it plus 1. All right, so it's a 3. We come down to this line, return, count, go find count. Count is a 3, so we return count, 3 is returned. Same thing here, just the process again for 4. Does the same thing for 5. So, all right, so yeah, 1, 2, 3, 4, 5 are all printed out. So, yeah. Cool. All right, so let's, okay, so a common mistake when you're thinking about this is like, okay, why am I not defining the variable in here? So let's, I'm just gonna kind of walk through this for a second. So if I define the count, all I did, and I'll leave it here also for like reference, but all I did is I moved the count from the counters, like main scope, into this anonymous arrow function scope. So we're defining it in here. Okay, so what's going to happen is, okay, so system runs, creates a variable for counter, assigns it to this function. Okay, we come down here, create a reference for my counter function, and then we evaluate it to this. Okay, so we get the counter function, we go grab the counter function, and then we invoke it. So now we're in here, we come to line 1, it's just a comment, so we ignore it, come down here, okay, return. So we need to exit and then give back whatever's here. Okay, so a function definition is given back. So my counter function points to this definition. All right, so now we come down to the next line, there's nothing, we come down to this line. Okay, so my counter function. So let's go up, find the reference. What do you refer to? I refer to the result of this, which is this function right here. Okay, so we're going to invoke it. We have the parentheses. So we come up to the top of this function, line 1, no parameters. Okay, we come down in. All right, let's create a reference to count and assign it to the number 0. Okay, let's come down here, let's find count. Okay, so count is right here. Let's plus it. Okay, so now count is 1. Then now we're going to return, so the function's going to exit. Let's go get count. Okay, so go find where it's defined. Okay, it's defined right here. And so it's not here, this is not the definition, it's defined here because this is where we're using let or const or var. That's where we're defining the variable. So we're saying go find out where it's defined. And then what is its value? It's a 1, so let's return a 1. So this returns a 1. Okay, that still works. All right, so now let's come down here. My counter function. Okay, go find the reference. It refers to this function. So now we run it. Okay, so create a reference called count and then set it equal to 0. All right, so count plus plus. Okay, so now let's increment it to 1. Return count, return 1. This returns a 1. We come right here, do this again. Comes up, runs this function. Let count equal to 0, so we define it as a 0. Count plus plus, make it a 1, and then return 1. So you're going to see that it's just going to print out 1, 1, 1 every single time. Something else I want to point out too is that, yeah, so like you'd write let here because you think it's going to change each time, but then in this instance, it's actually just being created once and then like it's deleted. And so it's actually, you actually would just use a const here because it's never going to be, well, you're doing a plus plus, so you'd have to do it, make it let. But yeah, so you use let because you're going to be reassigning it. And so when you do plus plus, it's, this is what plus plus is doing. It's saying count is equal to count plus 1. And so it actually, it's like reassigning the variable. And so it actually, yeah, you can't do a plus plus on a const. Okay, so, all right, so if we were to now look at this, okay, so, but here's there was a little step that I skipped over that the computer's actually doing. So, so we come in here, we run this for the first time. We come in, all right, let's create a variable called count, assign it to 0. Now we come down, all right, so count plus plus, we increase it to 1, and we're going to say return count. Okay, so we return a 1. So at this point, when this function returns, there is nothing in our code anywhere that references this count. This count variable is isolated. The only thing that references it is another thing, or like 2 places inside of its own function. But nothing else has access to this count. And so what happens is count is garbage collected. And so we'll go into memory management in greater depth later on, but essentially what that means is that this count variable, this value that's living in memory, it's removed because at this point in the application right here, there is nothing that can access count in its new modified state. If we call my function again, it's just going to reassign a new count. But the old count that was made to 1, nothing references it anywhere. And so then it's garbage collected and removed from memory anyway. And so, but if we define it here, what happens is this function can reach out and modify this existing count. And so because there's another function that's out there that could potentially reach back in and run count, that reference is maintained. So this count variable is not removed from memory because it's not, it always maintains that connection. There's always that access. So, okay, let me make sure that I've addressed everything that's in the question. So why isn't counter 2 when you run my counter function? Because you've already invoked it. So the first time I run it right here, so right here when I do this, when I call counter, this function right here has not actually run. So this is like a definition. So if you think of like functions as like there's definitions, and then when you call them, like they've run. This function right here is not run yet. It's like we're saying a counter is going to return this pre-run function to here. So this variable references this pre-run function, and then when we invoke it, it's going to go in and then it's going to run it. It's going to run that set of instructions. Okay. Okay. Oh yeah. So I see that you guys straightened that out. So okay, cool. All right. Yeah, we're using let because counter is going to be incremented on, rewritten over and over again. Okay, so if you sever the links to a variable within a function from any other function, the program it automatically fed to the garbage collector. Yeah, so essentially the way garbage collection works, just at a high level, is if we'll go into the details for how it's doing it, like the methods and practices have changed, and if you don't have good garbage collection, then you have variables and or like values in memory that aren't getting released, and it like makes your program get slower over time and creates problems. But they use a pretty good method of it now, and well, it's great. And essentially, it's just if there's ever a variable in your program that becomes unreachable, and then like at any point after, like nothing can ever like reach it or access it again, then it's released from memory, and then that memory can then be reused for other purposes. So essentially, it's just if a piece of code or a variable becomes unreachable, or just like your code goes along, and then there's a point where generally it's like you just don't have to think about it with JavaScript. Like if like your variables, if you no longer need them, then essentially they're just going to get picked up and removed. Okay. All right. So I'm still a bit confused. If you invoke counter, the function is rand. So how should it be different when it's assigned to my counter function? You're good. So so counter is this function, but it returns this function. So my counter function is only calling this small piece that's highlighted. But then counter is this whole thing. So counter is this big function, and then when we call it, it's going to return this small function. So when we call my counter function, it's just invoking this like small little function that's right there. Okay, let me. Okay, so there's the counter function example. Okay, so const my counter function, counter versus const my counter. Okay, so all right, so if I were to do this, let's ignore all that for right now. So if I do that, let's see. So if I invoke that, so think for a second, just like think to yourself for a second, what is result going to be? It's like, think to yourself, what is result going to be right here? So internally make your educated guess. So saying my counter function is equal to counter. Again, notice like the point of this is there's no parentheses right there. Then we're going to say const result is equal to the invocation of my counter function. So then we are going to call it. And now we're going to log it. So just like be thinking, what do you think it's going to print? Right. And boom. So it's a function. It returned this function right here. Like here's our arrow function with count plus plus and return count. And so when we made an assignment to counter, we essentially made it so that way we have two variables that are referring to the same counter, like this like big function right here. So if I were to log my counter function right here, and then let's console.log counter. So I'm going to run this. So we'll run it, and we're going to see that these are exactly the same. So what this did is it made it so my counter function and counter are both variables that refer to this function. And so you see they both print out the same thing. And then, so we print that out. And then right here, if we invoke my counter function and then print out the result, we see there is that little function that was returned. So yep, yes, there's the code snippet. So all right, so again, counter is in higher order. It's a higher order function because it is returning another function. All right, so this is a pretty advanced concept when it comes to JavaScript, and a pretty advanced pattern. So this gets asked about in interviews quite a bit. Yep, exactly, Pat. Yep, that's right. So yeah, so counter returns a new function, a different function, and then that we're assigning to the variable my counter function, and then we're calling that new function a bunch of times. Okay, cool. All right, so that is the main idea behind closure. All right, and then let's see. Move on a second. Something up real quick. Okay. All right, so I'm going to walk through n Fibonacci real quick. You guys have kind of seen this a couple times, but again, it's helpful to to see it and have it explained a few times. So, all right, let's do const n Fibonacci. Okay, so all right, Fibonacci sequence. We're just gonna say 1, 2, 3. So sometimes I'll put like 2 ones, but 1, 2, 3, 5, 8. And so every number is the sum of the two numbers that precede it. So 3 is the sum of these two, 5 is the sum of these two, 8 is the sum of these two right here. So, so what we're going to do is we're going to pass in a number. So we'll say n. So we're going to return the nth number in the sequence. So, so we pass in a 3, then it should be 3. If we pass in a 5, we should get back an 8. Okay, so the simplest way to do this is with recursion. So again, a very, very important concept idea to understand with recursion is it's just iteration. It's just looping. Recursion, everything that's done with recursion can be solved using either a for loop or a while loop. So they can do the same thing. So it's just another way to loop. And so so you have a function that calls itself. There are times when it is more convenient to write a recursive function over a while loop. Once you've kind of trained yourself to think that way, the code can be more legible and easier to read. So when we get into data structures and algorithms especially, there are recursive algorithms that you'll be using. So we'll be learning about a thing called a linked list, and it's very, very easy to write a recursive function that searches through the linked list. And when we get into stuff like that, I think that's when recursion will begin to click more for you guys. Check matching leaves in this assignment is pretty tricky, but that's a you're essentially searching over kind of a tree data structure, and we'll go over exactly what that means later. But yeah, so interesting. No, that check matching leaves is actually an interview question that I was given for a job that I applied to. So my last job, that they asked me that in an interview, and I had to solve that. So just to kind of give you a sense for the types of questions that are asked in, for like more, like if, for like a junior role, they may not ask something quite that challenging, but anyway, it's just something that you guys need to be able to do. So, and anyway, week 1, all this stuff will be pretty easy, pretty straightforward once you've gone over it for you guys. Okay, so again, all right, so if we look at our for loops, so there's 3 parts in a for loop. We have this counter variable that we're using. We have this truth case, so as long as this is true, we're going to continue. And then we have I++, so we're moving towards a point where this will be false. If we do not ever, like, if we never reach a point, so like if I was just doing I minus minus, so what we're saying is I is 0. As long as I is less than 10, keep going. And then after each iteration of the loop, make I 1 less. So I is going to become -1, -2, -3. And so you can see we're going in the opposite direction. We're never going to hit a 10. So if I were to run this code right now, this loop would go indefinitely until I kill the web page. Because everything's going to like freeze up and it's going to be stuck because it's just going to go over and over and over again and it's never going to end. So, so anyway, that's what's so that's what's going on. So oh yeah, and so the question about traversing multiple layers of an object with recursion. So it's actually very similar to a. So it's actually very similar to what do you call it? Sorry, lost my train of thought. So it's very similar to the what was it called? The flatten problem, where you're going along, and if it's a number, you add it in. If it's an array, then you call itself on the array, the nested array. And so you're going to do the exact same thing with the object one. So you're going to go along, and if you have a key that like a value that's a number, then you just like do a check on it. If you find a value that's an object, then you're going to take that object and feed it into the same function again. And so that's the general process. But I'll walk through that. So, all right. So again, with a for loop, we have to make sure that we are iterating towards a case where the loop is going to stop. So again, so ++ will make it so that way I will eventually be no longer less than 10, it will become equal to 10, and at that point this condition is no longer true, and then the for loop ends. And so with recursion, it's iteration, and so we have to think of a point like this where it's going to stop recursing, otherwise it's going to keep recursing until the program dies, and so, or we kill it. And so it's referred to as an infinite loop, where it just like keeps going and going and going, and there's nothing that's going to get it to stop. So, so anyways, we have to think about a way like, what's a condition that we can have in the function that will make it so it will stop recursing. And anyway, what we're going to be doing here is we're actually going to go. Well, we're gonna take in n, and then we're going to be making it smaller and smaller, and we're going to be moving towards like 1, like moving towards 1. So, and we'll be doing addition. So, I'm sorry. The problems are pretty much the same. I should probably switch the order of them. N factorial is a little easier, a little more straightforward. I'm actually going to switch to that real quick. That doesn't change anything in my explanation so far. It's just a factorial. So if we have so like factorial of 5 is equal to 5 times 4 times 3 times 2 times 1. Yeah, and so any number that you have, I guess that's the example I wrote. in the comments. But yeah, so factorial of 5 is that number times every like integer below it, down to 1. So, all right, so what we're going to do is if we get a number, so like 5 that comes in, we're essentially going to be reducing it by 1 and like multiplying itself. And so we're going to reach a point where 1 is going to be a, like 1 is the end. Once we get to 1, we want to stop. We don't want to go down to 0, because if we multiply by 0, then our solution is gone. You know, it's our factorial goes to 0. So we have to stop once we hit a 1. So what we'll do is we'll say if n is less than 1, so if it's a 0, so if we hit a 0, then let's return a 1. So that'll be our base case. And then if that condition is not the case, then let's see, and we're going to do return n times n factorial. So this has to be exactly the same. We are calling the function from inside of itself. I'm going to say n minus 1. Okay, so and I'll walk through this in just a moment, but let's okay, so run this, we see 120. Actually, I wonder, let me see what that, yeah, I like the way that reads a little bit better. So, okay, so, all right, so here's what we're going to be, all right, so here's how this works. So with n factorial, we're going to invoke the function. We're going to pass in a 5. And I guess I could just write this as like equals 1. That should, it's just, we don't have multiple things that are recursive. Okay, so yeah, so it should just equal to 1. So if n is equal to 1, we're going to return a 1. Okay. So here's how it's going to start. So now let's, okay, so the system, it begins const n factorial, so we create a reference, we assign it to this function, come down here, okay, so we take factorial, create a reference, and we assign it to this. Okay, so n factorial, we go up and find the function, and then there's parentheses here, so we're going to invoke it. We pass in a 5, so we come up here, n is 5. All right, so then we come down in here, we ignore the comment. All right, so if n equals 5, so if 5 equals 1, okay, it doesn't, so we skip that. Then we come down here. All right, so then return n times n factorial n minus 1. And so we're going to say 5 times, and then n factorial of 4. So we're going to pass in a 4. So what happens is this right here is going to hang. It's going to wait, and it's going to be open until this expression is evaluated. And this expression, in order for it to evaluate, another n factorial has to be opened. So we have this one right here that's open now, and we have 4 that's passed in. So we come down in, all right, so is 4 equal to 1? Nope. So then we go 4 times n factorial of 3, and then this right here won't return until this right here is totally evaluated. And so we open up another function. And so, but in this one, it's a 3, we come down, it's not equal to 1, we have a 2, all right, so then it's going to call the function again. And so then we have a 2 that's passed in, it's going to come down, we're going to pass in a 1, and then we're going to open up another n factorial. So you see here, it's going to open up a lot of functions. So when we get in the call stack and stuff like that, you'll see how the call stack will increase quite a bit. This is one of the reasons why recursive functions they can be more simple sometimes, like surprisingly enough, than trying to solve things with loops. But it's actually generally more performant and better to use loops. But for simpler things, recursion will be a more ideal solution. But anyway. All right, so okay, so we get down to this bottom one. So we passed in a 1. So we're gonna come down. All right, so ignore the comment. If 1 equals 1, okay, it does, so return 1. So this function right here is going to close up. This is going to evaluate to a 1. All right, so now we're going to return, n, which is 2 times 1. So return 2 times 1, which is 2. So this right here is going to return, it's going to be a 2. All right, so now 2 times n, so which is a 3. So 2 times 3, which is a 6. So this will be a 6. This right here closes up. All right, so now return 6 times 4. 4 8 12 24. Let's see. So I have 24 right there. This closes up. All right, and then 5 times 24 is 120. So 24 times 5 returns. And so this right here is now 120. And then we log out factorial, which go up in reference. And so we print out 120. So this is the process that it's going through when we recurse. So it's a little bit different to think about. Yeah, so this is how we solve n factorial. So again, the key is you have to have a good base case, and then you have to be moving towards the base case. All right. Let me write this. Okay. All right. So let's walk through. I'm not going to walk through the solution totally, but I'll kind of give some general ideas for the the tree one. So check matching leaves. So what the object is going to look like. Let me. So this is what it's going to look like. So that indentation is funny when I set it in, but you're going to have a bunch of properties on it. It doesn't matter what their names are, but the properties are either going to be a number or an object. And so then what you need to do is you need to run along and check and make sure and check to see if every single leaf on the tree is the same. So right now they are. They're all either ones or objects. So like they're all ones. But if we came down here and like I don't know, this was y or whatever, and I put a 2, then this would not all be the same. This would not, then there's a property on this tree that would not be a 1, and so at that point you would return false. And so we're seeing if every single value on the tree is exactly the same. Okay. So the way that we do this is, iterate over the keys on object, generally, and then, you can store, find out what the first key is, the first non-object key. We'll find, first non-object. That'll be set equal to, and you might do that inside of the loop. It all depends, but well, as you're iterating over it, this is what you'll do. And so delete this. And then there we go. Cool. All right. So, so we're going to iterate over the keys on the object, and then if object key. All right, let's ask our questions, if at all possible, in the Slack channel. Okay. All right, because it's harder for me to get in and see them in here. I have to click a button to see them. So, okay. So if object key. All right, so what we're going to do is, so essentially we're going to check the value of it. So if object key is an object, then check matching leaves on object key. So that's the recursive part. So, as we're iterating over it. So if object key is an object, then da, 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 da. Find for, so, okay, and then, maybe out here you'd have like a leaf value, and then, if leaf value is undefined, set it to object key. Otherwise, check if leaf value is equal to object key. Return false if not. And then you just have to make sure that your false bubbles up to the top. But these are kind of this is the general flow of it. So you're going to just iterate over the keys. So, iterate over, X, Y, Z, XA, whatever. And then whenever you find one where the value is another object, then you're going to take that object and then pass it back in, and that's where you're going to do the recursion. And so essentially it's like as you're moving along, you're like going this, 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 and drop down, this, 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 drop down, this, drop down, this, drop down, this, and then you'll like come up and then check this. So that's kind of the path you're going. So this is called the depth first search, because you see here, like we checked these ones, but then we went all the way down to the bottom before we checked this Y right here that's on the same level. And so it's a depth first search. So it's like we're going along, and if you find a hole, you go all the way to the bottom, and then you come up. And you are always like going as deep as you can. And this is a lot easier to write. A breadth first search is more challenging. Breadth first would be where like you search everything on this level, then you search everything on the next level, then you search everything on the next level, and like you're going down like this. But a depth first search is like you're going along, and then you drop all the way down, and then stay down, and then you come up, and then go back down again. So depth first search is a lot easier to write, and so that's just how we're doing it. But we'll go into that in a lot more detail later. Okay, so again, I'm not going to solve this one for you guys, right now, but just kind of explaining high level how you approach it. So. All right. Okay, cool. So yeah, this one is the leaves one. I mean, if you're sitting there thinking about it and you play with it, it's not too bad. And I think that it's definitely a simpler recursive problem. And like as far as like these types of problems, it's like, I mean, in some ways you could argue that this check matching leaves is easier intuitively to figure out than maybe even like n factorial. Just like so it's kind of different. Another way too is sometimes you have functions that will have recursive functions inside of them. So instead of like maybe making check matching leaves recursive, you might have another function inside of it that is the one that's doing all the recursion. So like for example, all of this stuff right here is inside of a recursive function that calling. This is a common pattern as well, and there's nothing wrong with this. So it's like the leaf value gets stored out here, so that way it's not being overwritten over and over again. And then we define a recursive function, we do all these steps inside of it, and then we're going to call a recursive function here. Okay. All right, so this leads me to a little side note. When you're working through problems, a very, very good practice is to kind of define it like this. So like, kind of writing out your pseudocode or your general instructions, like try to, first you need to understand the problem. Make sure you understand what it's asking, understand what you need to solve, and then try to break it down into high-level steps, how you would solve the problem. Try to figure this out, work through it, make sure it's good, and then translate this to code. And at that point, the coding part should be the easiest part. It's harder to do this when you're first learning because you need to console log stuff and you need to kind of experiment with your code and play around with it to get used to it. But eventually, this is how you're going to be coding everything. You're going to figure out high level how to do it before you start writing code, and that saves yourself a lot of time. So like in the long run, you're going to write less code. It'll be faster. And because sometimes if you just immediately jump in and start writing code, you'll like code yourself into a corner. And anyway. Okay, cool. So let me, how should I do shift tab in here? Oh, hey, that works. So there's another code snippet for you guys. Okay, great. So I just wanted to, again, talk about recursion and closure, touch on those a little bit, do some solutions to some of those problems. And then we will be going over, anyway, so now it's back to project time. We'll be going over additional stuff later in the day. So, all right, thanks everyone. Get this updated, or this video uploaded for you guys right now, so you guys can go in and view it.
Hey, Ben, do you by chance have the recording from the Wednesday lecture that you did after Ryan's?
Yeah, I'll get that up for you guys.
Sweet, thank you.
Okay. All right.
Thanks, Ben.
Thanks, everyone. Talk to you later.
See ya.